Alrighty, so now we're going to go ahead and continue on with chapter 12. This is our part 2. So we're continuing on with first order reactions, talking a little bit about half-life. So we talked a little bit about this in chapter 22 when we were talking about the nuclear reaction, the nuclear chapter. So I'm not going to spend a whole lot of time here. I will remind you about the equations for the half-life of a first order reaction. This comes up sometimes in questions, and it's such an easy reaction, such an easy equation that you should just remember it. Remembering that this number 0.693 is actually just the natural log of 2. So if you have a calculator where you're able to easily get the natural log of 2, you don't have to remember 0.693. You can just remember the natural log of 2 over k, which is the half-life of any first order system. So it works for nuclear decay. It also works for any reaction that can be described as first order too. And you can also see that because this is first order, because it has a constant half-life, the time it takes to have is always the same. But that halving process, right? Each successive half-life is an equal period of time. So 2 times 1/2 is the same length as to the time 1/4, to the time 1/8. Same as with a nuclear reaction. In any process that follows first order kinetics will have this same model. And so that means you can also calculate how much time is left by simply having it a certain number of times, or raising a half to some certain power if it's a fractional one. That's still all that same kind of thought process still works here. So estimate the half-life for the decomposition of this gaseous at this. Okay. Again, we're not going to do a plot here where they read it off a plot. They give us what they get, but again, we're not pulling out charts and rulers to really measure all that for this class. So they say calculate the half-life from the rate constant. So we can use the equation, which they provide us here for the half-life, and plug in the rate constant that they give us, and it'll give us the half-life. Now, it will give it to us in the units that k is in. So if k is in reciprocal seconds, then that half-life will be in seconds. So then we'll have to convert that to minutes, if that's what the question asks us for. Make sure we're checking what units the question is asking us for. At 5 half-lives, okay, it will be 1/2 raised to the 5th, or 1/32. So they say here, calculate what is the concentration after 5 half-lives? Well, it's 2 to the half, 1/2 raised to the 5th times our number, which gives us this. And then they say here, how long will it take for the concentration to fall to 12.5? So it turns out 12.5 is an eighth, but if you didn't know that, you could still realize that as how many half-lives you might have to get to reach that. And again, you can raise this 1/2 to fractional powers if that gives you the correct answer. Like, you can think about this as not a whole half-life, and this half-life modeling does still work. That's something else just to keep in mind from a mathematical standpoint. We can think about the time taken for any first order system and count it in terms of its number of half-lives. So we could say something is like, for example, 3.3 half-lives. And then all we need to know is the length of a half-life, and that will give us that answer. So it's possible basically to model it without knowing the actual length of a half-life, because we know that half-lives for a first order system are always the same length. That's not true for 0 and second order and other systems, but it is true for first order ones. That's why we make this special aside to talk about it. So if you can convert any kind of percentage or whatever into a representation of a power of 2 raised to something, you could do this with like a log. You could take a log of a half. There's ways to do that. But I think the easiest here is just to realize that 12.5 is an eighth. And again, we'll see chapter 22 for more coverage of this topic, but you may see some examples of this again in the homework. They talk a little bit about a half-life for some decay process. I have this also in chapter 22. I've replicated it again here, and we'll briefly look at it just for the sake of review. But if you want a more in-depth coverage of this topic, it's in that presentation. Again, we have an equation, and it's the same as the equation we saw for first order reactions for chemical systems a little bit earlier, but this is the version in terms of radioactive decay, number of nuclei. That's why they use an N here instead of a concentration, but it still works. It's not anything really different. And again, they calculate the equation for a half-life, and it's the same as the one that we've already seen. And here's another example. We can say the decay constant is this. The decay constant is our rate it's the same as our rate constant. So we can plug that in and solve the same way we have. Typically, though, for radioactive isotopes, they'll put this in hours instead of in seconds, but again, the basic concept's the same. So for a second order reaction, this is one whose rate depends on either the concentration of a single reactant raised to the second power or to the concentrations of two different reactants, each raised to a first power. Or, in theory, you could have 3 and one's a 0, or somehow they could add up to 2. This is the simplest example where something just is related to the rate with it to the second power. Simplest version of this. So the integrated rate law for a second order reaction is right here. You should write this down. This is a put on your flashcards item, because anytime you're asked about a second order system, you're going to want to be able to plug in these answers and quickly get an answer for like how much is left at some time, given the times and given the initial starting. You can calculate that here. And again, you can plot this on a graph, but we're not going to worry too much about that. And there's an equation for the half-life, but you can see that the half-life now is dependent on the starting concentration. That's not the same as for a first-order system. For the first-order system, the length of a half-life is independent of the starting concentration amount. That's really what makes them always have the same, the length of a half-life is always the same kind of thing. Whereas this is not going to be the same, because if I start from T0 to the first half-life, this will be the starting concentration. But for the second half-life, now this will be the concentration at the end of the first half-life to cover the second half-life. So this length will change as each half-life occurs. It will not be a constant length anymore. That's just something else to note about second-order systems. So they show this, how the first half-life is here, second half-life is here, third half-life is here, so time is changing. Okay, each half-life is twice as long as the preceding one. So that's important. The length of a half-life is no longer constant. Each successive half-life is smaller by a factor of 2. And here we have a table that summarizes all the different relationships. Again, very important, table 12.4. You should write this down, make a special note of it, copy this, print this, put this somewhere while you're doing the problems and the homework, because this will be your reference to go back to find all the equations that you might need as you're learning them. Notice this is a constant half-life. Notice the book says not constant half-life over here. Okay, and this gives you a plot, but again, we're not going to really worry about the plots. Mostly you need the rate order, concentration, time equation, or what sometimes they call the integrated rate law. That's this one right here, the second one, and then a half-life equation. These are probably the most helpful parts. So they do this graphically. But again, we could just look at the data and we can get some idea of what's going on here. So we're thinking we should see some constant change with time, right? We don't know what the half-life necessarily is, but if we look here, we can see that somewhere after, about 200 some odd seconds would be when this would reach its half point. Maybe let's say that's like 250, okay? But then from here, it seems like it would be maybe a little further out, because if that was about 250, then maybe it would be about here, maybe? Maybe. So figuring out whether this is first or second order, we might have to do some more further comparisons of the data. I'm ballparking it just by looking, and you can see that it seems like it would be a little bit longer, right? The half-life would be somewhere in here, and then maybe it would be somewhere in here for the next one. And that might make sense. That might be kind of reasonable if this was first order, okay? But we would also want to look at, are these changes with time constant? You could mathematically review these further, but we'll look at this in another quick step here. So they plot these to see what's going on here. And they say, okay, well, this looks like it's second order. But again, it's hard to see that sometimes just from looking at the data, like I was saying. Maybe it's a little bit stretched further. It's not always exactly clear. And you can see how plotting it might be really assistive. Again, I'm not going to give you anything like this that requires plotting. It's either going to be really obvious what's connected to what, or I'm just going to tell you, because plotting this is very tedious. So then they get the rate constant based off the slope of what they plot. Again, I'm not going to have questions that require you to plot this. I just want you to see that it's possible to do that. So they can calculate the concentration. Once they know that it's second order. It's really just plugging into the known equations to get the half-life, to get the integrated rate law, and then to finally calculate something else that they've asked you to do alongside with the rest of the problem. So that gives you some idea of like how you would do this. But again, analyzing a data set can be a little tricky because it's not always obvious exactly when these cut off from just looking at a data set, but you won't have anything where you're going to have to actually fully plot it. You might in a homework have to look at a plot, but that's going to be about the extent of it. Like I say, looking at the data, you can tell that there is some dependence on the concentration, but sometimes telling the difference between first and second can be more difficult than you might think. So another way to do it, if you don't want to plot it, is just to plug them into the relevant equations and see if you can predict what the value should be at a given time, given what you know about the modeling of the order, okay, and see if the relationship could actually be constant. Given, compare two different points or something like that. Again, you're not really gonna have to do that for this, but just give yourself some idea of how you could approach it. So when you have a zeroth order reaction, right, that means that you don't have any dependence on concentration at all. These are typically easier to see when you have a data set like that because you'll see a constant rate. You won't see anything that changes with the concentration amount. You won't see any kind of half-lifing that is constant like a first order or anything else like that. But that's typically a way you can kind of check. Again, they give you an integrated rate law for it, and they'll give you a little half-life, a way to calculate a half-life too. Again, the slope is constant because the rate stays the same. But there are instances where these kinds of reactions come up, like where you have a catalyst or you have some kind of surface where somehow the exact concentration of the reactants doesn't actually affect the rate because something else is more important than that. This is a cool example, but other than that, we're not really going to worry about it. Okay, so the next section talks a little more in detail about collision theory, which we brought up a little bit earlier in our discussions, right? This idea that reactions are driven by collisions, and so that's why we saw this concentration dependence, because if we had fewer molecules moving around, then we have fewer collisions, so the rates would change, right? The rate would be slower when there's less stuff. That's typically what we expect. We don't see that with zeroth order, but we see that with all the other orders where there's a dependence on the actual concentrations in place, right? So what does that really mean? I mean, what does it really mean for systems to be driven by collision? So they give us some examples where we could assume that some reaction takes place when two things hit each other. When a molecule or an atom hits something else, then the electrons have a chance to rearrange and things have a chance to reorganize, and then products are able to be made. So that electrical process is really fast, but the two things hitting each other is slow. That's the idea in the collision theory. That part's slow. And they also have to apply the right way. So if you have some big complex molecule, it may not be able to hit the other reactant in every possible angle and still react. It might have to come in from one side or hit it at a particular angle. And not only does it have to hit it with a particular angle, it has to hit it with enough energy. So they actually stay together so that the electrons can reorganize. Naturally, neutral molecules and atoms, they kind of repel a little bit. Repel might be the wrong word, but they're not attracted to each other. Their electrons will kind of bounce off each other if there's no reaction that can really take place, or there's not enough energy to get them to reorganize. So we have to think about the fact that there is this, now sometimes reactions can occur between things that don't have these filled shells of electrons, which is what the book is talking about. Sometimes there'll be ions that are electrically attracted to each other, and that can drive a reaction a different way. Sometimes they don't have fully filled shells, and so there are electrons that can stick to other electrons. So repulsion doesn't per se always happen, but they do tend to bounce off each other. And you need something to have enough energy so that when they hit, there's energy for the electrons to reorganize, and then a reaction happens. And that process, depending on the reaction, might release energy, and then that energy could carry on to the next steps and fuel some kind of reaction process, right? There's a barrier, and this barrier is the activation energy. That E of A, that's that activation energy. That's the energy with which they have to collide in order to drive this. And we can model this energetically by saying that When they collide, they form this transition state, and that's what they're talking about up here. So A collides with this molecule BC, some atom A collides with BC, and then they temporarily form this transient transition state here, which is unstable, and then the transition state decays into AB and lets C go. This is energetically unstable, and so this collision has to have enough energy to transiently form this so that then it can decompose into this. That's where the activation energy comes in. It's the energy required to push the system into the transition state so that then it can fall over here. Assuming this is a reaction where, it's going to release energy, it's driven by that factor. There can be other things that drive reactions, but we're going to assume that to keep it simple here, right? If this collision doesn't have enough energy, then it won't happen. Or if this collision occurs on the other side of the molecule, then maybe that won't happen either. We'll talk about that. That's a kinetic or a orientational energy that we'll talk about a little later. But this is where the E of A comes in. Transition state or an activated complex. So they give us a little diagram that shows this idea. The reactants come together, they form some transition state, and then they fall. And this delta E is the actual difference between the energy of the reactants and products. For something that is exothermic, it releases energy, or exergonic, to be more specific. It may not have to be heat per se, but E of A is energy is released. But we have to create this transition state first. So this is that E of A. It represents this. Okay? And the higher this E of A is, typically the slower the reaction is, because a smaller fraction of atoms and molecules have sufficient energy to actually drive the reaction. So experimental evidence from the collision theory comes from collisions of gases and kinetic molecular theory and the ideal gas law, but we don't have to delve into that per se. But there are a whole lot of collisions that go on every instant between molecules in the air per se, but only a small fraction of them could actually drive some kind of reaction, and that's what they're talking about here. So this Arrhenius equation, and we'll talk about this, there's another formulation we'll see, models that idea by saying that there's some fraction of molecules that have enough energy and we represent that energy as their temperature, right? Because they don't, individual atoms and molecules don't have temperature, they have a speed they travel at, and that speed they travel at, we can represent that as the temperature. Because that's their average kinetic energy for the ensemble, for the whole set. And we can use R here, R is the gas constant in joules, to integrate this E of A here with this temperature so that we can get a fraction of what amount of the set. So this F is multiplied by the number of molecules you have to give you the proportion that have that energy, given the kinetic molecular theory assumptions. So typically it's a small number, so they say, okay, well, if you have 7 collisions in a trillion are sufficiently energetic to produce these products. But again, these collisions happen so often that typically things are driven, but this is also a very high activation energy. 75 kilojoules per mole is really high. And a lot of reactions don't have barriers even that high. So, but this is more like realistic energies. This is the kilojoule scale energies, like me moving things around on the table levels of energy. And typically we don't need that level of energy for a lot of chemical reactions. So at a higher temperature though, so this is another way we can get around this problem. If we heat the reaction, then we'll get more collisions with a given set of molecules and atoms. So we just need to make sure that we have raised the temperature enough to kind of compensate for this. This is why some reactions are driven better if you heat them, those that follow this kind of model. I'll give you an example. So like paper oxidizes, it reacts with air and yellows over time. It's burning slowly. But if I put it in the oven at a higher temperature, you can prematurely age paper. And we're not trying to burn it, we're just aging it, crisping it up, yellowing it a little bit. You can do that because at a higher temperature, reactions proceed faster. And this process can be really significant depending on the reaction, right? And that's a way we can supply this E of A through temperature in a way. That's what we're thinking about. We're increasing the proportion of collisions that have this energy by increasing the overall temperature of everything. It's kind of a brute force way to do it, but at least it makes sense intuitively that we can supply the E of A that way. So again, we're looking at this reaction. We've got this state, but because we don't have the collision going the right way, this first reaction doesn't happen. We need an orientation as well. Many reactions require the correct orientation or they don't happen. Things just bounce off and no reaction happens. So they call this a steric factor. You can also think of it as an orientational factor. That's another word that the text uses. But this is usually really small for more complex reactions. So that means that even fewer reactions, fewer collisions will result in interactions. Again, the good news is that we have so many molecules and atoms, like multiple moles, trillions and trillions and trillions, that the number of collisions they have is so high that even if it's infrequent, it can still happen. We're able to kind of law of large numbers our way out of the fact that these collisions have a lot of requirements to them. Typically, for most systems, we can law of large numbers our way kind of out of these problems. So now we can add this all in to our reaction process. So if we think about this as like the collision rate related to some collision frequency for a second order process. So also, the higher the order gets, if you need more collisions to happen, like not just 2 things to hit each other, if you need 3 things to hit each other at once, or 4 things, it becomes, your rates of potential reaction drop dramatically. So you're typically looking for reactions that actually happen are typically only between 2. So one thing hits another thing, or one thing falls apart on its own and doesn't require a collision. Most reactions that really happen without a lot of assistance just do those things. Collision frequency is unit of second order. The reaction rate's lower because you've got this factor, P times F, because only a fraction have the correct orientation and the minimum energy. So you have to have this orientational factor, and then you also have to have the F factor that we were looking at, times this collision rate, which is how often these things actually collide. And you can see how all these can add up and can greatly diminish the number of successful reactions. The good news is that each time it happens, it's not like it's a failure. They can find each other again and hit each other again. And sometimes they'll bounce off a few times, and then eventually they'll hit the right way. So, and that can happen very quickly. Once atoms and molecules are in the right proximity of each other, they can bounce off each other a number of times and eventually kind of find the correct way to hit each other. It doesn't have to be like that. So we've combined all this together into an equation for the rate constant for some reaction that gives us the fraction of collisions, the steric factor, this collision frequency, and then the Arrhenius component over here that allows us to calculate the fraction of collisions with enough energy for the reaction. Okay, the Swedish chemist Savant Arrhenius, who also has the Arrhenius acid-base theory, it's the same guy, he came up with this equation for reaction rates. And sometimes they collect all these terms together as A, which includes the collision frequency, the fraction of collisions are both included together in this A factor. This A factor is just some other independent factor that's independent of the energy of activation. And again, this gas constant, you got to remember that this one's in joules. So you got to make sure you have that, because typically activation energies are provided in joules. Temperatures are in Kelvin, because temperature's in the denominator. If we remember that from a 151 class, you got to remember that that's true. Okay, sometimes they call this the pre-exponential factor or the frequency factor A, which is related to those other two variables. Again, so let's go ahead and stop here then. I think we've covered everything that we're looking for, so I'm going to go ahead and end our recording for now, and I'll see you again in the next one. Thanks.